All right, so like I said, and I'll just see, again, seeing the attendance, I think what I'll do is essentially make it, if you're a Monday student, you are guaranteed a seat in this room on Mondays. If you're a Wednesday student, you're guaranteed a seat in this room on Wednesdays. There's a lot of open space, so if you're a Monday student that wants to come Wednesday, and my guess is there'll be plenty of room, and vice versa, if you're a Wednesday student that wants to come on Mondays, that'll work out. The exams are graded. I have a number on top of everybody's exam. I want to just go through it, make sure, double count my math and all that. And so I'm going to bring it to lab. I will bring your exam to lab tomorrow, and if you're not in lab, if you're not supposed to come to lab, you can just swing by my office. I'll be around from like 2 to 3 or so, for sure. And then I'll bring them Wednesday. I'll just start carrying them around with me.
But they haven't been posted yet?
I haven't posted them. Yeah, I'll probably post them this afternoon, or this evening, or tomorrow morning. You know, counting's in the news these days, so I just want to make sure I didn't bungle anything too much. All right, so if you were in class on Friday, well, last week we talked about the addition of HX, right? And we're gonna protonate HX. Sorry, we're gonna protonate the alkene with HX, and we're gonna get the most stable carbocation. So all the reactions that go through a discrete carbocation, that means a free carbocation, are gonna always go through the more stable of the two options, right? So we have a choice of a tertiary or a secondary cation. We're gonna make a tertiary cation. And then the Br will attack the cation. And so this is just the reverse of an E1 elimination. Okay. On Friday, I showed this reaction, the oxymercuration. And you do not have to know this mechanism. Okay, I might ask, so you're fresh out of exam 2, you saw mechanism questions. That top reaction could be a mechanism question. This oxymercuration won't. But what happens is, right, the pi bond is going to attack the mercury, but now the mercury, unlike a proton, right, the mercury can bond to two different, it can expand the octet, it can bond to two different atoms. And so instead of getting a discrete free carbocation, we get this we get this mercurinium ion, where the positive charge resides on the mercury. It makes those two carbons really electrophilic. And then there's a couple of steps here, so this isn't the whole mechanism. All right, water is going to attack the more substituted carbon, and that's a weird bit of thing. It's going to attack the more substituted carbon because that carbon has the greatest partial plus. And eventually then you'll lose a proton and you'll get this alcohol, and then the overall reaction, if you take this oxymercurinium compound and you treat that with sodium borohydride, you just end up with a Markovnikov addition of water. Right, but it's a way to add water without going through a free carbocation, so that in this case it wouldn't be a big deal, but in some cases that addition leads to significant rearrangement products, and so this way there's not going to be any rearrangement here. So the reason you would use mercury in this reaction is to minimize how much rearrangement happens. All right, that brings us up to where you ought to be. So the next reaction is a reaction you haven't seen yet from me, if you should have seen it in the book or the PowerPoint. And this is going to be the anti-addition of two BRs. I don't like writing plus an enantiomer. This is going to be racemic. All right, right? And I'll walk through this mechanism. But the reason to have that, that mercury up there at the reason to have the oxymercuration reaction is this bromination reaction, this halogenation reaction works pretty much the same way. Right? So it's a little strange. BR, that is like, so on exam 1, actually in any exam, if I asked you if the bromine-bromine bond is polar, you should tell me no, right? You've got two identical atoms bonded to each other. But if you think about, right, so nucleophilicity increases as you go down the periodic table because the atoms get more polarizable. These bromines are really polarizable. Right? It's a weak bond. And if something with electrons comes up, it sort of pushes the other electrons down to the other end of the molecule, and so you get this instantaneous dipole. Right? If all the electrons go to one end, then the other end is going to be positive. So you get this, the bromine is actually quite polarizable there, and so you get an instantaneous dipole. The pi electrons react with this. You break the bromine-bromine bond, and now, you know what, I should have drawn this. I'll redraw the product here in just a second. So now, but this works just like the mercury. This attack, the bromine is not a hydrogen, so the bromine can bond to two different atoms at the same time, and you wind up getting a halonia line. And again, this is going to be racemic. This molecule is now chiral. The one we're working with is now chiral. And this is the one that sets the stereochemistry. So, right, an achiral alkene that's planar comes in. It's going to react with Br2. That's obviously achiral. The pi electrons can kind of sit down on top of the Br, or it can come from the other side. It can come from the top or bottom, front or back. Doesn't really matter. That bromine can end up above, below the plane. It's one atom, so anytime you have one atom like this, right, one atom has to be on one side of the molecule. That one bromine can't be both above and below. So the second step, so this is an intermediate. You can't isolate this. The second step, and the reason we get anti-addition, so now I'm going to put some stereochemistry in here. Let's say the bromine came from the back. So then both of these bonds, right, the bromine has to be behind the plane of the board. So now the mechanism is SN2-like. So the bromide is going to come from the back side. I guess it's coming from the front side, right? So it's the back side of this bond. I should have turned my bonds around the other way. So the bromine is behind, so this bromine is behind the plane of the board, so the bromide ion has to come from the top. All right, so the bromide ion is going to be out. This bromide, once we break that bond, is still going to be behind. And so the two bromides have to end up anti to one another. They have to end up trans if it's on a ring. Okay, so this will give us, we're going to invert that chiral center. Okay, so if you treat an alkene with X2, this works for Cl or Br2. All right, this winds up Cl and Cl. Questions about the stereochemistry first?
Originally, you drew it like this one's back and this one.
That's the enantiomer.
Okay.
Right? So again, this is racemic. Her point, I couldn't remember which one I drew. and I was pretty sure I had reversed this, right? So when I initially put this product up 3-4 minutes ago, this bromine was back, that bromine was out. That's the enantiomer of what I've just drawn. You get both of them. This is going to be a racemic product. All right, there's nothing in here. In order for this not to be racemic, this step, or the addition step itself right here, there would have to be some reason for the bromine to only come from the top or only come from the back, or mostly from the top or mostly from the back. Yeah.
The only thing I'm kind of struggling with is like the backside attack. How is it racemic with a backside attack?
Well, if the stereochemistry were as shown here, like if I had just this enantiomer, it wouldn't be racemic.
Oh, okay.
The point is we got 50%. The wedges and the dashes here are pretty much showing the relative stereochemistry of the bromine and the methyl. Right? So the bromine's out. If the bromine is out, if the methyl is out, the bromine's got to be back. If the methyl were back, the bromine would have to be out. And then the attack here is a backside attack.
So is that mechanism specific to that enantiomer?
No, it would be for either enantiomer.
Okay.
Right? So the point is, and the thing you need to know, these two BRs are going to be anti to one another. If it's on a ring, that means they'll be trans.
Is this just called anti-addition?
It's anti-addition. The two ways to add are going to be anti or syn. In an anti-addition, they're going to come from opposite sides, right? The first bromine comes from the back, the second one's then got to come from the front, or vice versa. Syn addition, SYN, is going to be, if the first bromine comes from the front, the second bromine comes from the front, or both back. There are other addition reactions where it's random. Okay, if you know which, one atom comes in from one side, that doesn't tell you anything about the second atom. That's pretty rare. So usually you either get anti or syn addition. So if it's X2, Cl2, or Br2, it will be anti-addition. Kind of the weird thing here, this is also, the same thing is true here. The Br, it doesn't really matter, right? The mechanism doesn't really matter which carbon you hit here. We'll see a reaction which it does in a minute. The nucleophile is going to hit the carbon that would be the better cation. That is, the more partial positive atom gets attacked. And this is a little, I don't know. I think maybe too often I try to anticipate what confuses you guys. Because it's always, when I do that, when I'm anticipating what confuses you, it's not you, it's me. I'm telling you, when I took Orgo 1 many years ago, here's what confused me. And the thing that got me is, this is essentially an SN2 mechanism. Right? So you guys know these arrows. It's an SN2. But the nucleophile is hitting the more substituted side. So the attack is happening like it's an SN1. Which is, I found that confusing, right? It's an SN2-like attack. That would make you think it should go here, but instead it goes there. Like I said, for BR, if you're going to end up with two BRs or two CLs, it doesn't matter which side gets it. Which atom gets attacked. But we'll see a reaction in just a second. You might be wondering about I2. So if you think about this, right, we're going to break a carbon-carbon pi and a Br-Br sigma. And we're going to make two CBr sigmas. All right, so for chlorine and bromine both, this reaction, the bonds get stronger going to the right. That's really true for Cl2. All right, so chlorine, the carbon chloride bond's really strong. And so making two carbon chlorine sigma bonds, that's very energetically favorable. For bromine, it's favorable. It's not overwhelmingly favorable. And this reaction can be reversed. All right, so if you take a dibromide like this and heat it up, like really pump up the heat, you can actually make this reaction go backwards. It's not a practical, the kind of heat we're talking about is not practical in a lab, but you can do it. For iodine, Same thing, we're gonna break a carbon-carbon pi, we're gonna break an iodine-iodine sigma, we're gonna make 2 carbon iodide sigmas. Carbon iodide sigma, remember, iodide's a really good leaving group, right? One of the reasons iodide's a really good leaving group is the carbon iodide bond is really weak. Okay, so making 2 carbon iodide bonds isn't energetically favorable enough to drive the equilibrium to completion. If you mix I2 and an alkene, you generally get kind of a mix of both sides, which is a mess. All right. I'm going to work my way up the board now.
Wait, so are you going to do the iodine one now, or is that?
No, I'm going to do a related reaction.
Okay, so for the iodine, it's just.
The iodide, you can't really, yeah, I2 won't give you the final product.
Oh, it won't give you it at all?
You'll have an equilibrium like 3 times as much as the starting material is. It'll be in there, the diiodide will be in there, but the reverse is actually pretty favorable.
Okay.
But I'll show you iodine, so this is halogenation down here. This is called a halogenation reaction. We're adding X2. We're doing that in an anti-fashion. All right. The next reaction is called the halohydrin. So, all right, this is going to add, we're going to add X2 and either water or an alcohol. So one thing that adds is X, and one thing that adds is OR. Let me put up an example. Same, we'll just stick with our methyl cyclohexene. So remember, I said that so iodine definitely adds. It's just that the reaction doesn't go to completion. So I2 adds, you get this iodonium ion, and it stops there, or it can reverse, or it can go forward. So again, let me spell this out. All right, so the pi bond is going to attack the iodine, break the I bond, and we'll get the racemic iodonium ion. And now down here on the bottom, the halogenation, when the nucleophile is iodine and we get 2 Ci bonds, that reaction doesn't go forward. But now we have a better nucleophile. We have water. Water is both a stronger base which means it's a stronger nucleophile. Really, those 2 statements mean the same thing, okay? So the carbon-oxygen bond that we're going to make is a lot stronger than a carbon-iodide bond. The other thing to think about is water is a solvent. We have a lot more water than we do iodine. Okay, so once we get to this intermediate, we have a whole bunch of water, right? And so now you can tell which carbon gets attacked. And again, this is going to be a backside attack on the more substituted carbon. So SN2 like arrows, and SN2 like stereochemistry, but on the carbon that you would think of doing SN1 with. Right? Still not quite there yet, because you got to take this proton off. And again, this is going to be a backside attack, so let's say the methyl comes out. Trans. Positive, I already put a positive on there. So, sorry, I'm going. I kind of get drawing mechanisms and I just like start flying. Sorry. Yeah.
So can you explain what you wrote in purple and how that relates to where the gains go with hydrogen?
Yeah, let me get to the product and then, yeah. All right, so this intermediate, and I guess having now looked at all the exams, I want to point this out. There was a problem. So there were two different questions. There was a problem about, so it's always, you have to figure out what nucleophile attacks, and is it neutral or is it negative? And in general, right, if you see an OH in a molecule, you want to have hydroxide attack. That's what everybody always, it's like, there's an OH there, if I just have OH minus attack, I'll get what I need. But if you don't have a base to make hydroxide, then water is the strongest base you have, and when water attacks, it's going to stay protonated. Right? So if water attacks here, it's not going to just spontaneously lose a proton. So make sure you include that proton. So then the last step is water taking this proton at the end. Your final product here is called, this would be an iodohydrin. Right? There's an iodide and an OH. So you've added I. If you come over here and look, you've added I and you've added OH. So an X and an OR. The OR is going to go on the more substituted carbon. And it's the same mechanism as the bottom. Right? So alkene's going to attack the X2. You're going to get this halonium ion. So a 3-membered ring with the halide having a positive charge and being bonded to both of those two carbons. And then a nucleophile, if there's only X2, the nucleophile is going to be the X minus. Sorry, people are writing fingers. I'm going too fast. All right. So if there's only X2 in the reaction, the only nucleophile you have available is this X minus. If you run the reaction in a nucleophilic solvent, even a weakly nucleophilic solvent, then the nucleophile that comes in is going to be the solvent. And so your question about, can I explain the purple comments, right? You're here, at this point, right, we have water and we have I minus. So which of those is going to be the nucleophile? 6 minutes. Well, even if there were just 1 and 1, like if you had equal amounts of water and iodide, which one of those is going to be the nucleophile? The better nucleophile, right? The stronger base. So water is a stronger base than I minus. You can figure that out. HI is a strong acid. So if I dissolve HI in water, I get H3O plus and I minus. So water is the stronger base. And then the other thing is, so that's, right, so water is a stronger nucleophile than I minus. So that's going to suggest that water attacks here. The other, the CO bond is stronger than CI. I'll get to that in a second. But we don't just have 1 water and 1 iodine. Water is the solvent. So we have 1 I minus. We have a sea of water. Right? So really there's water everywhere here. Immediately surrounding this molecule, right, the cage around that iodonium ion is probably like 30 waters. Just the solvent cage. Right? So now, you know, it's the thing I always try to use with students. This reaction, I'm the iodide, you guys are the water. Right? If a million dollars, if a bag full of money dropped into this room, is a student or a professor going to grab the money? Probably odds are a student. You guys move faster. You're younger. Your reflexes are better. Your muscles twitch faster. I'm older, slower. So, and there's only one of me. There's a bunch of you. So in this case, I don't know if that's a good analogy or not, but in this case, water or whatever OR is, Like this doesn't have to be water, it could be methanol. Right, so if this were methanol, right, so if we did use methanol as a solvent, then our product over here would be OCH3. If it was ethanol, it would wind up O-ethyl, whatever. You get OR anti to the I. Now this other statement about the CO bond being stronger than the CI, this reaction does go to completion. So down here, same thing, we're going to break a carbon-carbon pi. We're going to break a bromine, or up here, an iodide. I guess I'll go ahead and write it. So we're breaking a carbon-carbon pi and an II sigma. And we're making a CO sigma and a CI sigma. That CI bond is still weak, right? Carbon iodide bond is still pretty weak. But now instead of two of those, we're making one carbon oxygen sigma bond. That's really strong. Really what this is saying, the fact that you can't just add I2, this bottom reaction doesn't work with I2, is because really the CI bond is about the same as the carbon-carbon pi bond. Right? Carbon-carbon pi bond's much weaker than a carbon-carbon sigma. It's about 60%. The carbon-iodide sigma bond is about 60% of a carbon-carbon sigma bond. Yeah.
But the halohydrin reaction, that's not at all unique to iodine, right? You could also have
Right, yeah. I was just showing it with iodine because I want to emphasize that it happens. You could use Cl2, Br2, or I2 in this reaction. Like most any reaction in organic chemistry, almost all of them, if I say a halide does it, I do not mean fluoride. Fluorine chemistry is really weird. There's a couple of reactions you'll see in Orgo 2 where fluoride participates. But in general, fluorine is bizarre. All right? They're actually not so much anymore. But for a long time, there was organic chemistry, inorganic chemistry, and there was, people would identify themselves as a fluorine chemist because it just sort of existed off on its own. It's why, so we'll take a little break for a second. Like Teflon. Teflon is Teflon because of the fluorines in it. I think it's Scotchgard is what, the fact that 60 years ago, if you had a white carpet and it got dirty, like you were screwed. Nobody wanted a white carpet because, think about a carpet, it's going to get dirty. But now you can put stuff on the carpet fibers. You can just wipe stuff up. I've cleaned blood, like dried blood off a carpet, no stain. That sounds way more spooky than I need, right? Like I've cut my foot and blood on my carpet. And that's because we put a highly fluorinated coating on the carpet fibers. Stuff doesn't stick to fluorine. Fluorine is really, really strange. So you can't do either of these reactions with F2. And F2 is also super toxic. All right.